Welcome to the Space Telescope Public Lecture Series. Tonight's lecture, Supermassive Black Holes in the Centers of Galaxies by Darshan Kakkad. I am your host, Dr. Frank Summers of the Office of Public Outreach here at the Space Telescope Science Institute. And as always, I want to thank the wonderful tech team, Thomas Marufu and Grant Justice, who work behind the scenes to be able to help us present all of this to you and get it out to everybody on YouTube. I also want to note that the Space Telescope Public Lecture Series will continue to be online only through the rest of 2023. Our upcoming lectures on March 7th, we have a lecture on active galaxies. I'm not exactly sure what aspect of active galaxies Travis Fisher is going to talk about, but he has promised me an abstract in the coming weeks, so we'll find out. But some aspect of active galaxies, Travis Fisher here from STSCI. On April 4th, Catherine Bennett will be talking about understanding planetary habitability using exoplanet atmospheres, looking at atmospheres around other planets and seeing, hey, could they be habitable? On May, we have an even more indeterminate lecture. Amanda Pagul has said that she's going to give a lecture, but she has two different topics and she hasn't decided which one. But again, I will push her this month to try and give me at least a topic by ready to talk next month. And if you want to find out after she does give me a topic, what that topic is, you can go to our website, www.stsci.edu/public-lectures. You'll get to our public lecture series talk page, and on the lower left, you can see the link to our webcasts. We have got recorded webcasts on YouTube back to about 2015, and we have a webcast archive at Space Telescope. I think that goes all the way back to like 2005, okay? So if you want more public lecture series, we got you covered, right? Also in the lower right, you can see the easiest way to get reminders of it. Just put your email address, hit that subscribe button, and you'll get 2 or 3 emails a month reminding of the upcoming lectures and letting you know when the webcasts have been posted. Also on the website are the list of our upcoming lectures. And if you click on any of those lectures, you will get the details, including the speaker in the description, as well as after it has been broadcast, links to the STSCI webcast, as well as the YouTube broadcast. For email, as I said, announcements to sign up at the website. You can also subscribe to our YouTube channel, youtube.com Hubble Space Telescope. That will give you notices of new videos and reminders of live events such as this one. And finally, if you have comments or questions, you can send them via email to publiclecture@stsci.edu. Our social media at Space Telescope does for the Hubble Space Telescope, for the Webb Space Telescope, and for our Institute on Facebook, Twitter, YouTube, and Instagram. You can see them pictured there. As always, say I do a tiny amount of social media on Facebook and Twitter. And now our news from the universe for February 2023. Our first story tonight, the weight loss plan of cluster galaxies. And you say, Frank, you're just being silly. And I say, yes, I am actually being a little bit silly, but I think it means that you're going to remember it, okay? So first of all, let's talk about cluster galaxies. There are these giant clusters of galaxies, hundreds to thousands of galaxies that are all orbiting around one another, okay? And as these galaxies agglomerate, the galaxies will pass through the cluster and around the cluster, and they orbit together within this cluster. Now, when that happens, all right, they actually encounter something called ram pressure stripping. I'll say that again. ram pressure stripping. Okay, that means is the galaxy going through the cluster hits the intra-cluster gas, and sometimes some of that gas will sometimes bleed out material. It'll strip out material. All right, and so this galaxy here is called a jellyfish galaxy, not because it's swimming in the ocean, but because it has these tentacles streaming off from it. And that is a result of ram pressure stripping. You can see these blue stars, these streams of blue stars moving all in the same direction. All right, and if you actually pull back from this galaxy, you look at it in X-ray light. The X-ray light shows you this big gas streamer of material that's being pulled off this galaxy as it's moving through this intra-cluster medium. Okay, so this is an example of how the material in a galaxy can get stripped out of that galaxy and become part of the cluster itself. All right, and so if you've got a large cluster such as this one, this is Galaxy cluster Abell S1063. It's a large galaxy cluster. And if you look really, 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 really closely with Hubble, you can actually tell how much light there is in the cluster that's not due to any galaxy, but is due to all this stripped material, okay? This intra-cluster light. And so Hubble measured it for S1063, and here is a map of that intra-cluster light in 1063. Okay, so galaxies lose material as they go through clusters, but the question that we're going to address today is, which diet plan do they use? Is it a quick weight loss plan, i.e., does the galaxy cluster have to develop to a certain size and the intracluster gas have to be certain density before this ram pressure stripping is effective at pulling stuff out of it? And if that's true, well, then the intracluster light should only appear recently in the history of the universe. However, if it's a slow burn weight loss plan, that means the idea being that the ram pressure stripping, of course, and some other things like galaxy merging, is effective in removing material from galaxies right from the beginning, as the cluster is forming to begin with. Well, then that intracluster light will appear gradually over the course of over time. So, what they did with this program is they looked at 10 galaxy clusters at different distances out into the universe to see whether or not this intracluster light was there late in the universe, or mid in the universe, or very early in the universe. Okay, and so here are 2 of those clusters. They have serious phone number, catalog numbers there. And you can see they map the intracluster light from them. We call them ghost light galaxy clusters because, you're looking really down into the depth of the light here. I mean, this intracluster light is like 1/10,000th the light of the galaxies, okay? The galaxies are 10,000 times brighter than this intracluster light. So you're really looking at a very faint signal. But hey, this is Hubble. Hubble can do this. And what they found is that it's actually this slow burn weight loss plan, that the intracluster light is there proportionately all the way back to the galaxies that they see. So why? We're not exactly sure. It's ram pressure stripping, there's mergers and other things that can pull things out of galaxies. But in understanding how galaxies form into clusters, there is got to be some process that removes stars from these galaxies that happens all the way along through the history of the universe gradually. It's not one big thing happening all at once. It's a gradual process all along the history of the universe, and that teaches us something about the formation of these big galaxy clusters. Our second story for you tonight is the many portraits of NGC 346. Ah, yes, you're thinking, oh, good old NGC 346. What is NGC 346? Well, this is the Small Magellanic Cloud, which is one of the 2 major dwarf galaxies orbiting around our Milky Way galaxy. The Large Magellanic Cloud and the Small Magellanic Cloud. Yeah, we astronomers, we call them as we see them, right? Large, small. Okay, and in the Small Magellanic Cloud, it only has one significant star-forming region, and that is NGC 346. Okay, and this is a valuable star forming region to look at because all of these stars are about 210,000 light years away. So they're all at the same distance. That gives us a good measuring stick to be able to judge all the stars in there together. All right, so we've looked at it several times, and Hubble back in 2005 released this image of NGC 346, this beautiful blue image. And then also in 2005, really only 10 months later, we've released this beautiful red image of NGC 346. I was here in 2005, and I remember that we did these two images in the same year, but I'm still, to this day, I'm not sure why we did them. But also, after doing this red image, we also, in that same press release, released this black and white image of 346. So Hubble, on its own, really from one major observing program, was able to get three, count them, three portraits of NGC 346 that highlight just slightly different aspects in each one of them. Well, you can guess where this is heading. We now have the Webb Space Telescope. So now we're going to get the ultimate infrared portrait of NGC 346. And here is Webb's portrait of NGC 346. And it is really, really cool. Okay. I mean, this is actually, what is it? It's like 40 million pixels. Okay. There's a serious number of pixels here. There's a lot of cool detail here. But what I'd like to do for you is show you some contrast between the Hubble and Webb images so you can understand why we have more than one space telescope up there, okay? So on the left is the Hubble image, and on the right is the Webb image. And you can see that they are significantly different. In particular, take a look at this region here. All that gas and dust that appears in the Webb image is barely visible in the Hubble image. And at the bottom of that region, there's sort of in the Hubble image, you can see there's a cluster of stars. We're going to zoom in on that, okay? All right, and so in the Hubble image, you can see that cluster of stars. But in the Webb image, you don't really see the cluster of stars so much as you see the gas that it's embedded in. This is the warm gas that the near infrared picks up so well. If we go to the main cluster in the center of the image, you can see Hubble picking up this really cool, just unbelievably bright cluster of stars. But the exact same Webb image doesn't really feature the stars. Again, it features the cool gas and dust. And this is just a lot of fun. I went blinked back and forth like a dozen times as soon as I put this together this afternoon. It's like, okay, there's Hubble and there's Webb. Okay, yeah, Hubble and Webb. All right. So you see the two brightest stars in the infrared here. Okay. Do you see those in the Hubble image? Yeah, they're probably there, but they don't stand out at all. Whereas the brightest star in the Hubble image, if you go look at it in the Webb, well, it's there, but it's not particularly, excessively bright as it is. And this ridge of gas and dust up here, okay, this stuff here in the center, that's all drowned out by the star cluster. You don't see it. Whereas the ridge down here that you see a bit in Hubble, all right, comes across in gangbusters with the Webb Space Telescope, okay? So this is a fantastic example of why we have both visible light telescopes and infrared space telescopes, so that we have two different views that show us two different sets of conditions and teach us that much more about what's going on in the universe. All right, some people mistakenly say that the Webb has replaced Hubble. And I hope that this shows you that Webb doesn't replace Hubble. Webb complements Hubble, and Webb provides an alternate view that gives us different physics and different science and more knowledge about the universe. All right, so our speaker tonight, Darshan Kakkad. Welcome, Darshan. He is only been with us at the Space Telescope Science Institute for a little over a year. He joined in January 2022. And actually, Darshan, do you have an office in the building? Okay, you do. Okay, because some people who joined during the pandemic have never actually been had never actually been inside the building when they gave a public lecture. Great,
Oh, I come every day.
great. I only come in once a week, so Darshan got his PhD in Munich. And then traveled around the world. He went to the European Southern Observatory in Chile before going to Oxford, England to do studies there. And then he ended up here at Space Telescope Science Institute last year. That's actually, one of the times after you get your PhD and you do postdocs and you transfer around till you finally find your permanent job, is one of the more exciting times in astronomy because you have the opportunity to travel the world. And Darshan, it's great that you've taken advantage of it. To present a little bit more about him, he told me that he likes to do outdoor activities, in particular running and hiking, and that he also likes cooking, especially proud of some of the cakes that he's made. So, ladies and gentlemen, Darshan Kakkad.
Thanks a lot, Frank. And I suppose all of you can see my slides.
Yes,
Great.
we can see your slides.
Okay, and you can hear me well as well, correct?
Yes.
Great. Okay, thank you. So, good morning, good afternoon, good evening, everyone, wherever you're joining from. Thank you very much for joining this public lecture series on supermassive black holes at the center of galaxies. My name is Darshan Kakkad, and I'm a postdoctoral researcher here at the Space Telescope Science Institute. Often when I hear the word, whenever I say the word black hole, people often think about these sci-fi movies, and especially the movie Interstellar that came out a few years back. These black holes are really powerful objects. So how do we know that they exist? How do they form? Do these black holes have any relevance in our daily lives here on Earth? So these are some of the things that I will touch upon during this talk today, and I hope that I'm able to convey how fascinating these objects are. So now, before we dive into the world of black holes, we need to understand at what point during the timeline of the universe did they become relevant. So the video that I'm about to play here shows you how the universe began from Big Bang and how it evolved from there. So yeah, I hope that this plays. Yeah, good. So there was a Big Bang, right? And soon after the Big Bang, the size of the universe increased dramatically, which we popularly call as the inflation of the universe. And after this inflation period, the increase in the size slowed down and the universe became dark. We call this phase as the dark ages in cosmology. And the reason that we say that it's dark is because there was just gas over there. There was no source of light. There were no stars. There were no galaxies. Nothing except for the gas. And this all changed roughly about 400 million years after the Big Bang. 400 million years might sound like a lot of years for us, but then in terms of the cosmological timescales, it's really small. So yeah, roughly about 400 million years after the Big Bang, when all the gas then clumped together and formed the first stars, and these stars then grouped together to form the first galaxies that we know in the universe. And these stars and galaxies then evolved and ultimately gave rise to the familiar-looking galaxies that we see today, including our own Milky Way, similar to the galaxy that you see on the screen right now. So this slide here shows you a picture format of what you just saw in the video. So the timeline in this picture increases from left to the right, and the size of the universe is depicted in this vertical scale here. So we start off from this very, very tiny point right here. So that's the point of the Big Bang, and then the universe expanded very rapidly, followed by the Dark Ages, and right about like 400 million years after the Big Bang, we had our first stars, the first galaxies. And as I will show you over the next 1 hour, It is exactly during these times when it is believed that some of the first black holes came into existence in the universe. And we are here, roughly 13.7 billion years later. And it is through the technology that we have developed and our understanding of the physics over the last few hundred or even thousand years or so that has allowed us to make this kind of a picture that you see in front of you. So, in order to understand how black holes form, we need to understand stars. Because, as I will show you later, black holes are basically formed after stars die. So, first of all, how do stars form? So, we start off with this sort of dark cloud. So, this dark cloud consists of atoms, molecules, and dust, and so on and so forth. And due to gravity, the cloud then compresses and starts forming these kind of clumps. When this cloud is about, say, 10,000 times the distance between the Earth and Sun, so that kind of size, we start calling this a pre-stellar core. So pre-stellar core is something like, which is dense in the right center, and the density then falls off as you go outwards. Stellar means stars, pre means before. So that means that this particular cloud that you see is now in the process of forming a star. So at some point, the pressure inside this cloud becomes quite large, and large to such an extent that the atoms inside these clouds then start fusing into each other, and they produce a large amount of nuclear fusion energy. And this energy is then visible in the form of light. And during these stages, like when the nuclear fusion happens and the gas cloud is there, any excess gas and dust is just ejected along the poles, and it leads to the ultimate formation of a near flat disk. So in C, D, and E here, that is exactly what you see. So the light from the star basically just removes this, just ejects all of these gas and dust along the perpendicular direction, and then you're left with this disk along the equatorial direction. And so what happens is that the star still keeps growing from the material that it takes in from the disk, but then there's also ejection taking place at the same time. And depending on what stages a star is, you would call it a protostar, T-Tauri stars, pre-main sequence stars, and so on and so forth. But the final result is the star right in the center. It's called a pre-main sequence star, where you have a star in the center, and then there are planets surrounding that. Now, let me tell you that this whole process takes about tens of thousands of years. Certainly, we are not going to live that long. We will all be gone within the next 100 years or so. So we individual human beings are never going to be around to see this entire whole process happening one by one. So what we do is we take pictures of multiple objects and try and piece them together to get a complete picture. So over the next few slides, I will show you these pictures that we have taken from telescope, both on the ground and in space. So here I'm showing you an example of the clouds from which stars form. So this is quite a famous picture from Hubble Space Telescope that was already taken back in 1995, so roughly about 28 years ago. So the structure is called Pillars of Creation and shows these multiple elephant trunks. And the reason that we call this as Pillars of Creation is because the gas that you see here is in the process of creating new stars. But at the same time, some of this gas is also being eroded by recently formed stars. At the time when Hubble took this image, it really started shaping the way we see how stars form over millions of years. So then, of course, like recently we've had the Webb Space Telescope, and we went back and took an image of the same gas cloud, and voila, we actually started seeing dust as well in between those molecular gas clouds. Now, dust is a major ingredient of star formation, and what we are seeing at different places are the lava-like regions which capture periodic ejections from the stars as they form. So this was basically the formation of stars from the dark clouds. But then here's another example of the next stages of star formation, protostars that, again, Webb Space Telescope captured very recently. So the star right in the center makes a fiery hourglass shape in its infancy. So basically, at this point, the star here is clearing out all the gas from its polar regions, as we saw in this cartoon picture here. And this entire system is actually on its way to becoming a star. Now, remember that since it is ejecting out material, so you see this kind of a jet of streams, like streams of particles coming out. So it's not just forming stars, but it's also preventing formation of new stars there. So in a way, what's happening is that it's clearing out any gas. So the star is kind of marking its territory right here. So in the end, the protostar has all the gas around in these regions and the dust materials just for itself, and it doesn't really have to share it with other stars. And so, as I said, like in the final stages, what we get is sort of a solar system. So a star right in the center with a system of planets around it. So this is a very familiar looking picture that we know from our own solar system. So systems like these exist throughout our own galaxy. Even in the Milky Way or in the galaxies around the universe, there must be millions and millions or even billions of solar systems. And the laws of physics are the same, no matter whichever galaxy we reside in. So here's a video of, which kind of shows you the formation of stars from the gas clouds and how they all come together to form a galaxy in the end. So what you can see is that there are these streams of gas. There are these sort of like these fireworks that goes on in this video. These fireworks are basically very new stars which are being formed, and these stars then come together and sort of make these kind of galaxy kind of shape that you know from many astronomical images in the media as well. So at least now you get a rough idea of like how stars form, the beginning of the star life, but then obviously we are here to study black holes, but I'll soon come to that. But we want to know like how a star evolves then. So we just saw how an average star forms from a molecular gas cloud. Now most of these stars have their fuel as the hydrogen atoms. They are fusing into each other, right? Now what happens if, say, the star runs out of this fuel? At some point this can happen, right? That there is nothing left to fuse into each other. So that's when the red giant phase of the star comes up. So this happens when the entire fuel for star formation is consumed and the outer envelope expands. And the reason that we call this is a red giant is because the star appears redder during this phase, and it's really, really big. Really big to the extent that if sun were to become red giant, and it will become red giant, not if, it's a question of like when the sun becomes a red giant, it will become so big that it will actually swallow Earth, Mars, and part of the asteroid belt as well. So just imagine the size of sun at that point. I mean, Earth would just completely disappear by that point. Fortunately, that's certainly not going to happen, at least all of the people who are watching this video are alive. So yeah, the star becomes a red giant, and then what's next? So the outer envelope just keeps expanding, and in the center, the star keeps getting compact and compact, and it radiates ultraviolet, and it keeps radiating ultraviolet light. Remember, we all apply these sunscreen lotions. That's basically to protect ourselves from the UV radiation from the sun. So the ultraviolet radiation from the stars, it keeps coming on, and it lights up this envelope that is expanding on the outside. And the result is one of the most beautiful phenomenon and one of the most beautiful pictures that you can ever obtain in the universe. And that is a planetary nebula. Look at that. A small star right in the center, and that lights up all the gas that you have from the star's atmosphere. Actually, the name planetary nebula is kind of a misnomer because it has nothing to do with planets. It got its name because these were round, shaped like planets when the astronomers observed these things with the early telescope. So in this particular image, you can see like the Webb Space Telescope images of Southern Ring Nebula captured with the telescope quite recently. And then once this envelope disappears, all you're left with is a small white dwarf, and that is the end stage of this particular star, a particular set of stars. Now, I'm not here to tell you exactly about stars, as I said, we are getting there towards the black holes now. So, and the good things come at the end, of course. So what if this initial star was much, much heavier? So what if the star was, say, 10 times the mass of the sun? Then the first two stages essentially remain the same. That is, we still get that star, we still have the red giant phase, only except this time there's going to be a red supergiant phase, because, things are bigger now. We have a much heavier star. But instead of a planetary nebula, because the star is so heavy and big this time, we end up with a supernovae explosion. So a supernovae explosion basically is visible from the Earth, or even if it happens in galaxies other than the Milky Way. And after the supernovae explosion is over, we are left with two possibilities. And one of those possibilities is a neutron star. So here I'm basically showing you a blinking picture of these two images. One taken before the supernovae event and one taken after. So let me keep this for a few seconds over here. So can you tell where exactly is this explosion? It's right here. So this is what we astronomers do most of the time to detect a supernovae. In order to see a supernovae explosion, we take multiple images of these galaxies, and at some point we see this kind of a boom, a burst of light that comes from one particular point in the galaxy. So after the things have cooled down with respect to the supernovae, we end up with this neutron star, so neutron is a subatomic particle. Within the nucleus within the nucleus, we have protons and neutrons, and in neutron star, the particles, the neutrons, they just pack themselves so densely. They don't emit light, but this kind of a star spins, and they have a very strong, intense magnetic field. And so if there are charged particles, they get trapped in this magnetic field, and they start emitting light. And you can basically detect these light in the form of these periodic patterns, very similar to the lighthouse that you have in the seashores. Now, if the initial mass of the star, so the massive star, was, say, roughly 25 to 30 or 50 times the mass of the sun, then we don't get a neutron star because, the packing has to be even more dense now. So the star still goes through a supernovae stage and everything like that, but now it leads to the formation of a black hole. Not a neutron star, not a white dwarf, but a black hole. So finally, after what we've seen so far for the past 15 minutes, how stars form, how they evolve, I hope you know how a black hole actually forms at the end. So let me tell you a bit of a history about black holes first. So the concept of black holes was already introduced by John Michell back in 1783. So as it was postulated, he was thinking of a method to determine the mass of a star, and he accepted the Newton's theory of that light consists of small particles. Now imagine that you're throwing a ball up into the air while you're on Earth. Obviously, the ball speed will be maximum when you're throwing it. It goes up to a certain height, it slows down, it stops, and then it falls back again. By that time, people knew that light was extremely fast, and if light was also a particle, then it should kind of behave like what I just told you about the ball right now. So John Michell said that there could be a case where there is a star, basically, and it's so massive that even the light cannot escape that star's gravity. So that star must be invisible because, there is no light reaching us at that point. There's no light escaping that star. Of course, this was just a concept at that time, and the term black hole itself did not exist until then. No one really used the term black hole at that time. The real foundations of this concept of a black hole started after when Albert Einstein developed the general theory of relativity in 1915. Einstein developed a new paradigm that defines how gravity works, and his entire theory is based upon tensor calculus. In the words of John Wheeler, Einstein's theory can be summarized as follows. Space-time tells matter how to move. Matter tells space-time how to curve. Now remember, we are talking about 1915, a time of war. Karl Schwarzschild was in Germany, like he was a German physicist and an astronomer, and soon after learning about Einstein's theory, he developed solutions to Einstein's equations. And one of the features of Schwarzschild's solution is that for very compact, high-density stars, so they were still calling stars at that point, remember that, because black holes still did not exist. I'll come to the point when we started calling them black holes. But there could be these high-density stars that it could become much harder to escape the gravitational field of that star, that even the light cannot escape through it. At the event horizon, which is basically the point of no escape from the black hole, time slows to a complete standstill. It's very similar to the concept of like Interstellar movie when Matthew McConaughey approaches the black hole. And so physicists at that time, basically because of this concept that, the time stands still around the event horizon, so the physicists called these bizarre objects frozen stars. So the general relativistic principle is sort of depicted here. So basically, we are living amidst a space-time fabric. And in the presence of mass, the space-time curves. It's quite similar to like if you have a rubber sheet or like a piece of cloth that you would stretch out, and if you put some mass on them. So the heavier the mass, the greater is the bend. And so if a light particle travels through this, not light particle, but the light waves or particle, whatever, it doesn't matter at that point because light has this duality. So if light travels through this fabric, it bends and then it changes direction. So the more heavier the mass is, the light curves further, and if this curvature is too intense, like in the case of black hole, even the light cannot really come out of that particular hole. At the end of it, it can't really escape from that ultimately. So the term black hole actually was popularized by John Wheeler during a lecture he gave at NASA Goddard Institute of Space Sciences here in New York back in 1967. And as we know it, the term black hole is used so frequently when we talk about space, in science fiction movies, etc., etc. Well, at least in my life, I use this term quite regularly now. Almost on a daily basis. So remember, like we are talking this about like back in 1960s, we still did not have a detection of black hole. This was a concept, a very strong one at that, but still we needed to develop methods of detecting these black holes. 10 years after Einstein's death, Roger Penrose, now at Oxford University in the UK, he proposed critical mathematical tools to describe black holes. He showed that Einstein's theory meant that black hole formation must be seen as a natural process in the development of the universe. And for this, Roger Penrose was given a Nobel Prize in Physics just 2 years ago, along with two other astronomers who I will describe in a few minutes. So by the time it was 1960s, it was pretty much clear that black holes should exist. We had a very strong theoretical foundation for it. I have, of course, not described the gory details of the history, but then just to give you an idea of like how things progressed over the last 100 or 200 or even 300 years or so. So now what was left is we had a theory that black holes should exist. We needed to build telescopes, develop state-of-the-art instruments that would help us conclusively say that black holes do exist. So over the next part of the talk, I will show you what we have been trying to do to detect these black holes with observations. And using these observations, we have been confidently be able to say that what a black hole should look, what the area around the black hole should look, and so on and so forth. So this picture basically shows you a cartoon model or a schematic model of how a black hole and a region around the black hole looks like. So right at the center, you have this singularity. The edge of this black area is called the event horizon. And the black holes also have these disks around it. So through that disk, it eats up the material from the interstellar medium. And in some cases, you would also have a jet that comes out of these black holes as well. So the black holes can come in like three mass ranges. One is stellar black hole. Their masses are anywhere between about 10 solar masses to about 100 times the mass of the sun. Then we have an intermediate mass black hole, which is anywhere between 100 times the mass of the sun to about a million or less than a million, like 100,000 times the mass of the sun or so. And then we have the supermassive black hole. So what I would do is, like, I will go this in stages. I will show you how we detect stellar black holes, how we detect intermediate mass black holes, and how we detect supermassive black holes. And remember, detecting these different kinds of black holes require completely different techniques, or maybe similar techniques as well, but then different techniques as well. So imagine that you wanted to weigh baking powder in your kitchen. You would not really go to your scale in the bathroom and then use that scale to measure, say, 1 gram of baking powder or something like that. You would obviously use a kitchen scale. So as a similar analogy, the method of weighing these stellar black holes or supermassive black holes, they differ depending on what kind of object we are looking at. So let's come to stellar mass black holes. Stellar mass black holes, as I said, that they are anywhere between, say, 10 or, but pretty much less than 100 times the mass of the sun. Now, let me tell you, in our own Milky Way, it's postulated that there could be about 100 million black holes or so. The problem is, it's difficult to detect them because they're black holes at the end of the day. We can't see them. I mean, you know, the space is dark, and then in between, you're trying to find this black object over there. So one of the ways that we can find black holes in the Milky Way is using gravitation waves. So this is again going back to the space-time fabric of Einstein's general relativity that we saw a few slides back. So here I'm showing you, say, two very compact objects. They are circling around each other. And in this process, what they do is they send out this ripple of waves completely outward, in the outward direction. And it is possible to detect these ripples on Earth, and that is using the LIGO interferometer. So here I'm going to show you a video like how LIGO works. So what happens is that there is a beam of light that goes and hits against a mirror, which then splits the light into two arms. So you'll see that one of the light goes in one direction, it hits against a mirror, comes back, and combines with the other light ray, and then we see how it looks. Now, if the path between this mirror and this mirror and this mirror was exactly the same, then what we would get is a combined light. That means a bright spot. But then in the presence of gravitation waves, what happens is that, so let me go back a bit. Yeah, let me pause right here maybe. There we go. So if these two paths were the same, then the combination would lead to a bright spot here in the detector. But then, because of the gravitation waves, the relative paths of this arm and this arm would differ, and due to which we'll see a change in the intensity of the light pattern on the detector over here. So when we see the change in the intensity, you see, like you can see the intensity changing. Using that, we can detect that, okay, there is a gravitation wave that we just observed. And using how much time it took for these waves to change these shapes and so on and so forth, you can determine the mass of the black holes, which are then ultimately combining or circling around each other. So here's an example of like the masses that we've measured so far using gravitation waves. So you can see that, you know, it's anywhere, say, up to 100 or even 200 or so, all the way down to even 1.5 or 2 times the mass of the sun. So coming to the next stage, which is the intermediate mass black holes, which are much, much heavier than the stellar mass black holes, but much, much lighter than the supermassive black holes. And this is the big question right now, that how do we detect intermediate mass black holes. Even astronomers are struggling right now, and this is a major challenge because we want to know where we can find these intermediate mass black holes. So it is postulated that there are these globular clusters. Globular clusters are these clusters of stars, and in between these intermediate mass black holes can be lurking around. And we might also find intermediate mass black holes in small galaxies right in their center. So as we saw, like the intermediate mass black holes can be determined using the intermediate mass black which I'll come to in a short while. And the last way we can detect is through tidal disruption events. So tidal disruption events is when a star is completely ripped apart by a black hole. I will show you a video in a while, but then this is what happens. So there is a star. Because of the presence of a black hole somewhere, it encounters that black hole and the star is basically ripped apart. Star emits light, right? So if we can trace that light path, we know that there is a black hole over there. So this is quite incredible, and it's very rare to even detect these kind of events. So now finally moving on to the supermassive black holes right at the center of the galaxies. So when I say supermassive, how massive are they? These supermassive black holes can be as heavy as 1 million to 10 billion times the mass of the sun. So just think about it for a bit. 10 billion times the mass of the sun. It's extremely heavy, and you can imagine how powerful this kind of a system can be. So the question arises is that how did they end up getting so heavy? How is it that these black holes have become this size? So remember I told you about the tidal disruption event? So this is how it happens. So the black holes grow by taking in materials from their surroundings. And so here, I'm showing you an example that, okay, here's a star, and there's a black hole somewhere, and then you can see how the star is completely ripped apart, taken in by the black hole. So there's this black hole right in the center. There is an accretion disk. This disk is where you get most of the material funneling into the black hole. And in some cases, you can also see these jets that are coming right perpendicularly out of the black hole. So this is one of the ways in which the black holes grow. This is one of the ways in which the black hole accumulates mass. And this is not just limited to supermassive black holes. This is limited to stellar mass black holes, intermediate mass black holes, as well as supermassive black holes. And this is also another way that the black holes can become supermassive, by combining two black holes together. So we often have these situations where there are two black holes circling around each other. And you can see that because of the fabric of space and time, you can see so all of these stars in the background, they start becoming fuzzy, or they start moving around a bit. And that's all because of the space-time curvature. And so we have just explored two ways through which the black holes grow. One is by the tidal disruption event, when basically a star is completely ripped apart, and one is by the combination of two black holes themselves. So another way of detecting black holes is through time series observations. So a few slides back, if you remember, I told you right here, high resolution time series observations of clusters. Now, this is an image of the very center of our own galaxy, the Milky Way. So over the last 20 years or so, using extremely high resolution observations from ground-based telescopes, what we've done is we've kept taking pictures of the center of our Milky Way. And what we've observed is this. As you can see, these stars seem to be rotating around this invisible object. Now, obviously, this is a perfect candidate that there is a black hole right there, and this is the center of our galaxy. So this was basically obtained using the very large telescope right in the middle of the Atacama Desert in Chile. If you ever get a chance to go to this observatory, I would highly recommend to do that. I worked here for about 3 years or so. I spent about 200 nights there. And what you do is you land at the airport, you then go right in the middle of the desert. There's no light. Even during the night, you have to drive a car down from the mountain over here. You're not allowed to turn on the headlights because even a little bit of light could contaminate your astronomical data. And it's one of the darkest regions on Earth. So in the middle of the desert, we have developed this, developed these state-of-the-art instrumentation that could help us in obtaining these high-resolution images so that we can see how the stars are moving around right in the center of our galaxy. So how do we obtain high-resolution imaging? High-resolution imaging is obtained using this technology called adaptive optics. So I'll just play this video here, which shows you how adaptive optics actually works. So obviously, when you have something on the ground, there is atmosphere. It's not really as dark as space. You have the atmospheric molecules, due to which the star then appears fuzzy. And what we want is to remove this atmosphere completely. So there is this technology there where it detects how the atmosphere is, and it removes the turbulence that the wind from different regions. So for example, like this technology is detecting what the atmospheric disturbance looks like. It replicates that, and then it corrects for it. And to do this for the center of our galaxy, two astronomers, Andrea Ghez from UCLA and Reinhard Genzel from Max Planck Institute in Germany, they did pioneering work by developing these technologies, and they shared the Nobel Prize back in 2020 along with Roger Penrose. And their work basically gave us the most convincing evidence yet of a supermassive black hole right in the center of the Milky Way. And that was a time series image that I just showed you a couple of slides back. And here's a sort of a cartoon, or rather a schematic diagram of what was happening in that video. So we have these different stars at the center of the Milky Way, and they're revolving around this invisible object. And this invisible object is basically the black hole right in the center of our own galaxy, the Milky Way. Now, obviously, we want to image the black hole. I mean, obviously, we want to get pictures of that. We have pictures of stars. We have pictures of nebulae. We have pictures of those protostars from which show these kind of nice hourglass shapes and so on like that. Why can't we take the picture of a black hole? And so this is what you might have seen, say, from the Interstellar movie, where there was this black hole right in the center, but then what do you see? This sort of a bright structure. This bright structure is basically the accretion disk. Remember, black hole's gravity is so strong that it curves space and time. So what you see on the top here is basically the accretion disk from behind the black hole. So it completely curves, the light completely curves from behind the accretion disk, comes towards us, and that's why we see this sort of a symmetrical structure. Now, obviously, this was a picture from the movie. This is a picture which is based on simulations. But can we actually take a real picture from our telescopes? And that is exactly what happened a couple of years ago using the Event Horizon Telescope. If you all remember, this was a black hole image taken from a nearby galaxy. And our own Milky Way looks like this. So kind of like this donut-shaped structure. How did we do this? So in order to make an image using any telescope, we want the telescopes to be much larger. Larger the telescope, the more zooming in you can see. It's very similar to the Nikon and Canon cameras that you use. The larger the size of the lens, the more clearly you can see those images. So what astronomers did was they used the Earth itself like a telescope. So we had telescope all the way down to the South Pole, in Chile, in the US, in Hawaii, in Europe, and in Greenland. And what we did was we combined the power of all of these telescopes using this technology called interferometry. So the data was recorded in hard disk in all of these locations, physically brought together. in one place to combine them, the data all together. So this is an image of some of the telescopes that were used to make those images. And so due to the fact that we've been able to combine the data from these telescopes, we were able to get these beautiful images of our own Milky Way using the data from telescopes all the way from the South Pole all the way to the Greenland. Now, as I said, in the title, the supermassive black holes at the center of the galaxies. So very recently, when I say very recently compared to the conception of the black holes, the conception of all of this theory. So what we found out was that the mass of the central bulge of the galaxy and the mass of the black hole, they kind of go hand in hand with each other. So that means if the black hole is lighter, the bulge of my galaxy is also lighter. If the black hole is massive, the bulge of my galaxy is also massive. And that gave rise to the idea that maybe the black hole is actually doing something to our galaxy. It's actually impacting the way stars are forming. So here's a schematic, or rather a video of how this might be happening. So what you see here is a black hole right in the center. And because of the accretion disk, there's a lot of radiation pressure. And due to this radiation, very fast winds start coming out of these black holes. So what you see in yellow here is basically the fast wind that comes from these black holes. And why is that happening? Because it is from the accretion disk. There's a lot of radiation pressure over there. And as a result of that, what happens is that this wind, and I'm talking about this, the wind speeds of 1,000 kilometers per second, is extremely fast, and only a black hole can drive a wind which is that fast. And what this wind does is it just clears out the galaxy completely out of gas. So basically, if there is no gas, there would be no star formation. So again, what the black hole is doing, the black hole is taking in matter, it is producing radiation, the radiation is then hitting against the interstellar medium, and that is driving the gas out of the galaxies. And what ultimately happens is a shutdown of star formation in the galaxies. The galaxies basically become dead. And it's all happening because of this black hole, which is taking in matter and trying to grow, actually. But at the same time, so as I said right now, that the black hole basically removes the gas from the galaxy, but at the same time, the black hole winds like these can also trigger star formation. So here's a video of one of the results that we obtained about 5 years ago. So you see that there's this galaxy here, and this is the outflow, or rather, these are the fast winds that are coming perpendicular out of the galaxies. And then you have these star formations. So I think you'll soon see that within the wind itself, there would be star formation happening. So this is the accretion disk. And from the accretion disk, you have the radiation. And we used basically the telescope in Chile, the picture that I showed you very recently. So you can see that there are these fast winds. They travel at extremely high speeds of 1,000 or even 2,000 kilometers per second. And you see these clumps right here. That's basically stars forming within these winds. So while these black holes can shut down star formation, it can also create the formation of new stars. It can also give rise to the birth of new stars within these fast velocity winds. And obviously, a lot of things changed on 25th of December 2021 when we launched the Webb Space Telescope. This really ushered in a new era in astronomy, because now we were able to obtain much clearer pictures, a complementary picture, but much clearer pictures of these galaxies, to the extent that now we can zoom in very close to the regions of the black holes to see how they look like. So this was the launch of the Webb Space Telescope, and this is one of the images of the nearby galaxy and a nearby black hole, actually. So you see a very bright center, and what we can see is that we can now peer through the dust. Because of the fact that the Webb Space Telescope works in the infrared, we can now look through the columns of dust that would have otherwise enshrouded the black hole, making it invisible. But now, in the infrared, it shines really bright. And so the Stefan Quintet is one of the galaxies, one of the set of galaxies that the Webb Space Telescope imaged. And what we can see is this detail of gas and dust interplaying with each other, and we can now see these details, which we could not basically even a year ago or so. So this is really, really incredible stuff that is now coming out of James Webb Space Telescope, and is also going to improve our understanding of how these black holes right in the center are able to affect our galaxies, and how would they look like in the future. But the story obviously doesn't stop there. At the end of 2020s, we will also have the Extremely Large Telescope. The Extremely Large Telescope, as you can see, I mean, we have a habit of naming telescopes based on their sizes. We have the Very Large Telescope, and now we will have the Extremely Large Telescope. And the Extremely Large in the sense that this will be the size of one of the football stadium. Imagine that, a telescope this size, the telescope dome, to be the size of a football stadium. So the Extremely Large Telescope and the Webb Space Telescope will kind of work together. They're not canceling each other out, but rather they're working together to uncover what lies right in the center of these black holes, what happens to the gas as it moves in, and how exactly those fast velocity winds that I had shown you is actually launched from close to the black holes. So I hope that I have convinced you that these black holes are fascinating targets, and over the next decade, over the next 10, 20 years, very easily, there's going to be exciting times because we have new telescope coming up, even more, both from the space telescopes as well as the ground-based, as well as from ground-based telescopes in Chile and elsewhere around the world as well. So I would like to thank you for your attention, and I would be happy to take any questions that you may have.
All right. Thank you, Darshan. That was very, very extensive coverage of black holes from the beginning of the universe to the formation of stellar mass black holes, getting into the intermediate mass black holes and up to the supermassive black holes. One of the questions that one of the points you made is Webb being able to see these active galactic nuclei. In particular, you talked about Stefan's Quintet. Now, I just did a visualization on Stefan's Quintet, and the galaxy with the big bright AGN, NGC 7319, has a honking big emission that Webb sees. But being a cosmology guy, it wasn't clear to me, where is that infrared emission coming from around the AGN? Is it the outer parts of the accretion disk? Is it the outflow material? I mean, to emit in the infrared, you've got to be cool gas. And I wasn't, and since I naturally associate black holes with high energy stuff and X-rays and such, where is the infrared emission coming from?
So if you talk about the black hole itself, so the supermassive black hole, so the infrared emission comes from two places. There is the far infrared that comes from the equatorial direction. So we have like the equatorial direction there, but the mid-infrared emission, which I think the Webb telescope might be seeing,
Yep,
could be coming in from the outflow, or rather these fast winds. So there's this dusty outflow scenario that is taking place very close to these black holes, and we have seen that in many other galaxies as well, where the infrared emission basically comes very perpendicular to the galaxies, and what we think is that is basically the dust from from the polar directions of these black holes, which is emitting in the mid-infrared wavelengths.
Okay, cool. Because I guess I had naively, not knowing this the subject matter, expected huge infrared emission from active galactic nuclei. And so it was something I was trying to learn about, but I was doing the visualization, and I didn't need to know, but I needed to know some of the material information about it, and I thought that was fantastic. All right, Grant Justice has been following the chat on our YouTube stream. Grant, would you like to join us and tell us if you found any cool questions on our YouTube chat?
Yeah, absolutely. I actually have a really good one to start us off. So, one of the viewers had heard that the Milky Way, supermassive black hole, is smaller than others, or is uniquely smaller than others. Is this true, or is there anything special about our black hole?
So I would say, I'm sorry, I would say that the Milky Way black hole is indeed smaller than many other supermassive black holes that I have personally studied. So Milky Way black hole is roughly around like 1 million solar masses or so, if I'm not mistaken. But then the black holes that I am looking at are roughly about 100 million or 1,000 or about 1 billion solar masses or so. So I would say that it's not special in that sense, because like there's always this bell curve, right? We'll always have a maximum number of galaxies with a particular mass bin. So yes, I mean, there is a black hole right in the center of the Milky Way. It is inactive right now in the sense that it's not as bright as a lot of other galaxies that you see, but it was at some point bright. And we know that from Fermi bubbles. So if you look at in the gamma rays, so just as you saw, like in the perpendicular, you have these two kind of like cone sort of structures. We can see them in gamma rays also. So the Milky Way is, I would say, is sort of a stereotypical galaxy. But then yes, its black hole is lighter than a lot of other galaxies that we see.
Yeah, but I guess my question, following on that, is the Milky Way smaller than it should be given its mass, right? Mm-hmm. We have a trillion solar masses in stars and dust and dark matter, et cetera, in our galaxy. Is the 2 million solar mass black hole what we should have, or should we have a larger one? And I wasn't sure of the answer to that.
Yeah. I would say I'm not too sure about the answer as well.
Okay. All right. So that relation you showed going from the stellar mass black holes to the intermediate to the supermassive, we're at the low end of the supermassive black hole range, as being just in a few million. But, we're also not the largest of large galaxies, right? So yeah. I wasn't sure whether we fit on the curve or whether we're below the curve or not. All right. Well, we'll have to look that up, and we'll get back to that person.
Exactly.
Is there any reason that we know of that it's smaller or not as bright?
I'm sorry?
Is there any reason that we know of why it is smaller or not as bright as you mentioned?
I think it could be so. It all depends on like how much mass the galaxy had to begin with, how much of gas and dust it was able to accrete during its formation. So, yeah, I mean, I don't have an answer to the fact that why it's smaller right now, not at the top of out of the top of my head.
You're good. It's your whole study. Yeah. Like that's why you have a job, is to find out these answers. So
exactly,
it's good.
Yeah. It's something of my homework then.
That's one of the things I love about working with scientists is if when you're presented with information you don't know, it's just more things to learn. Like, it's beautiful.
Ignorance is job security.
Yes.
All right. Okay, so I wanted there was a question about the LIGO results. Okay, and the implication being that LIGO has totally changed your field, right? Right. And so. if LIGO results had come out a decade or 2 decades earlier, the question was, how would that have changed where you would be now in your career or something? I mean, were they truly this step change, and is that going to be marked as a point where this changes everything?
Yes,
in the field.
definitely. It's just completely a different way of looking at the universe, right? I mean, we started off 500 years ago with these optical telescopes. And soon, about just 70 years ago or so, we started doing these radio observations. And that opened up a new era in astronomy. And then now we have we had X-ray telescopes, we had gamma ray telescopes, and now we have gravitational wave telescopes, which is just different in the way that it operates, right? So obviously, yes, if LIGO results, or rather LIGO operations had come out 20 years ago, 30 years ago, so my career could have been different in the sense that I could have been working on a completely different kind of telescope right now. And even, I mean, if you look at it, after the LIGO results have come out, I mean, we have Virgo and LIGO India as well, which might come up at some point. So the resources are then distributed. And the job creation is, or rather the priority is then to have more people working on, say, LIGO instead of, say, the other telescope and so on and so forth. But I would say at this point, what we are doing is that we are balancing it out. Like there's a group of people working on LIGO, a group of people working on optical telescope, a group of people working on space telescopes, and so on and so forth. So it's going to balance itself out, say, in the next 20, 30 years or so. So in short, yes, if LIGO results had come out 20, 30 years ago, there is a possibility that, yes, the career paths of most of the astronomers that we know of right now could have been different.
So a slight follow-on to that was that, I've only followed the LIGO results from afar. And, you showed one of the plots about all the different merger events they have. And I know that these runs are sort of staged and things. When do we think we'll have enough statistics really to gauge whether the expected merger rate, in order to build these supermassive black holes, there has to be this merger rate of black holes, with the expected merger rate, whether what we measure actually fits with the expected merger rate. Is that something we're getting a handle on now, or is it going to take another decade or two?
I'm not sure if it will take another decade or so, but then right now, yes, we are building up the statistics. We are right on that curve there. So at some point over the next few years or so, we might be able to say whether it's within the expected merger rates or so. But then there's also the challenge that these signals are so weak that we are trying to isolate those individual events within that noise, let's say the noise that we have. So there's a possibility that we do have that data, but the immense amount of effort comes in to detect those signals, to isolate those. Overall, I would say that to properly characterize the amount of merger rates and everything that we see could take a few years still.
Okay, great.
Okay.
What else did you find, Grant?
Sure. With TESS, TESS being a telescope, for those in the chat that don't already know, Google it. It's awesome. Astronomers have observed a ring of planetary debris with moon-sized structures in the habitable zone of the white dwarf star WD 1054-226. How could they have survived the red giant phase?
So that's an interesting question, and as a non-expert, I can answer that. That it's possible that you're looking at a planet which is, say, in the outskirts or so. So it's left relatively unscathed during this entire red giant phase. That would be my guess to that question. That it's possible that you're looking at a planet which is, say, in the outskirts or so, and that was sort of protected. Not even if it's not protected, at least it survived in its form.
I just get the image of like random fragmentation, like it's all just chance.
Yeah.
Further away, the safer you can be.
Perhaps.
Potentially, yeah. All right. Let me grab another one.
I have one.
Go ahead.
So you were talking about the black hole wind and having an effect on the galaxy itself. It just occurred to me when I was watching that, going to myself, all right, so we have a stellar wind, and that, can create a little bit of things, and only during like the T-Tauri phases that wind's strong enough to actually push gas out of the solar system, right? So is this black hole wind that strong and that dense all the time in these things, such that it really will affect on a galactic wide scale material in terms of this pressure?
Yes, I mean, compared to the stellar winds, I think the black hole winds are immense. I mean, you're looking at 2,000, even 3,000 kilometers per second sometimes, especially at a time in the universe when the black hole growth rate and the star formation rate was really maximum. So yes, it is possible for these black hole winds to affect the outskirts of the galaxy and not just at the vicinity, not just at the vicinity of the black holes.
Yeah. And does that act as somewhat of a limiter in terms of, like, if your black hole gets this big, it's going to blow out everything in the galaxy, and your galaxy can't get any bigger? That's
exactly
somewhat of the limiting effect?
Yes, that's the limiting effect, not just for the galaxy, but for the black hole itself. Because if the black hole is just removing all the gas, it's not getting anything for itself as well. So, it's a lose-lose situation both for the galaxy and the black hole. But then, hey, that's how we have maintained this sort of a balance, so to speak.
Like it's chasing away its own lunch. All right, what else do we have, Grant?
Sure. Little bit broader question. When you refer to center of galaxy in relation to other things, are you talking about center of mass, center of visible mass, or matter, center of motion? What does that refer to specifically?
I would say is the center, like the physical center, in the sense like when you look at the morphology of a galaxy, and I'm only talking about these nice spiral-looking galaxy, right? Yeah, that's like the physical center of the galaxy, which could be very similar to the center of mass as well, if you ask me, because I think at the end of the day, the actual morphological center, the center of mass, they would nearly coincide at that same spot, almost over there, unless you're looking at, say, an irregular galaxy in which even I would not be able to tell you what exactly is the center of that galaxy until we make some dynamical or kinematical analysis of the gas around that galaxy, right? So yeah, I would say that whether you're talking about the like the galaxies that I was showing, whether you're talking about morphological center or the center of mass or so on and so forth, they would nearly coincide with each other.
Gotcha. That makes more sense.
And just for our viewers, remember that when you talk about center of mass, it's not just the visible light, it's also the dark matter in the galaxy. And because the dark matter determines the gravity, that determines the motions, the center of mass and the center of motion, as our questioner put it, really are going to have to be the same thing, okay? Because the mass determines the motion.
Gotcha. And as you can see from the questions, we're on both sides of the spectrum from understanding, which I love about this. So bringing it back to another general question, what is it about black holes that makes it so hard to study, photograph, or capture data?
I'm sorry, can you repeat that question?
What is it about black holes that makes it so hard to study them? Why can't we see images, or why was it such countrywide, like worldwide news when we had captured an image or as close as we got of a black hole?
Right.
What is it about them that makes them so difficult to study?
So a black hole is a black hole, right? I mean, so there is no light coming out of it. So for example, like if I'm looking at, myself, for example, the reason that you're able to see me is that there is light coming out of this bulb here. It hits against my skin and then it reflects off onto the camera. That's why you're able to see me. Now, what if I switch off this light right now? Then obviously, like, it reduces. And if I switch off the other light as well, obviously, like, I'll get darker and so on and so forth. So in order to capture an image, you need the light coming out of that object. And in a black hole, if the light itself is not able to escape the gravitation potential, then what are we going to capture? We are basically going to capture something which is dark. So that's why it has been difficult to detect black holes, because there is no light coming out of them. And even if there is light coming out of them, that's from these accretion disks. And we have to wait for the appropriate opportunity when that accretion disk forms. And that emanates light. Or when a star is ripped apart, basically. We need to wait for those kind of moments. Or you make these observations for 10, 15 years, and then you see how the stars around the center of the Milky Way move. So yeah, I mean, definitely, it's a hard job because of that.
Kind of like what they use for exoplanets, where the transit happens, but the opposite. Instead of blocking the light, it's diverting the light, so it's the opposite effect on study, I would imagine. Because one is the absence of light, where the other is the brightness, and we're seeing where it's, yeah.
Exactly.
I mean, Grant, I think you've got an analogy there in terms of the exoplanet, the transiting exoplanet versus like microlensing, right?
The words aren't there, but I'm trying.
No, but I'm saying microlensing, the black hole passes in front of a star and it amplifies the star. It changes the star due to lensing and such. So that's an analogy I hadn't used before, but I think that might work. Hey. All right, so I want to actually question another thing that I don't know is the census of intermediate mass black holes, because I remember when we first announced, a decade or so ago, the detection of intermediate mass black holes. So like the merger rates, do we have a good census of how many intermediate mass black holes there are? Because I don't hear many discoveries of these intermediate mass black holes. I still feel like that's a big unknown in our knowledge.
Correct. That's correct. I mean, we know about supermassive black holes. We have just started detecting stellar mass black holes as well, using gravitational waves and so on and so forth. But intermediate mass black holes is this big unknown. I mean, for example, detecting, say, 1,000 times the mass of the sun, detecting a black hole with 1,000 times the mass of the sun. That's something that has not happened, for example. Or even if that has, so that's something we are not able to detect right now. And so the gravitational waves could be one of the ways to detect intermediate mass black holes, especially if you have 200, 300 solar masses or so on. But then other ways is actually what we did with the center of the Milky Way, that we track the star's motion every few months or every few years or so, and then we see how they move around. And for globular clusters, for example, if you do the same thing, you can look at the way the dynamic works. So that's the way of detecting them. But then the census-wise, it's a big unknown there. We don't know when we will be able to detect intermediate mass black holes in large numbers.
All right, great. All right, Grant, do we have like one more question?
Yeah, I've got a couple more if we've got time, but I can.
All right, I think we have time for two more.
Okay,
two more.
Sounds good. What, in your experience, has been the spread of sizes of black holes? Like, what is the smallest? What is the largest? What notable ones have you seen that you would like to discuss? There's always something that jumps out in the data to people.
Yeah, so I think like the smallest black holes that we've seen, at least detected so far, was with the gravitational waves, 1.5, 2 solar masses, something like that. The heaviest that we have seen is in the early universe, where we have detected up to, say, 10 billion solar masses or so. So that's the rough range that we are looking at, all the way down from 2 solar masses to about 10 billion or so. But I do believe that there could be even smaller black holes than what we have detected so far, or maybe heavier ones as well. But then, that's the limit that we have had so far through our observations.
Gotcha. And on the stellar mass black hole scale, we've detected a couple hundred solar masses. I know we've detected 150 solar masses with LIGO and Virgo and such. How large have we detected on the stellar mass black hole scale?
So I think it's up to just below 200, I think.
Okay. And was this expected to get 200 solar mass black holes? Because I'm not an expert,
yeah.
and I sort of hadn't expected that large.
Yeah, I mean, again, not working on LIGO, but I would say that this could have been accepted.
Okay.
Expected. Yeah.
Okay. Next
Gotcha.
question.
Sure. And we'll finish up on this one. I like this. Which came first, the star, the galaxy, or the black hole?
I would like to say stars. So, you know,
Okay.
I mean, we always had the gas, right? I mean, after the gas came the stars. After stars came probably black holes or galaxies. So yeah, I think I would follow that succession there.
Okay. All right. So this corollary to that is how quickly does the supermassive black hole form as a galaxy forms? If we looked in the early universe and we saw, a billion solar mass galaxy, right? Would it have the proportional supermassive black hole even early on, or is that going to take longer? How do they grow at the same rate that galaxies grow?
So that's interesting because, like, I think right now we are already debating like when the first galaxies and stars came in. And so how early on the black holes, or rather supermassive black holes came in is yes, it's a question right now, which
Okay.
I don't think we have an answer to. But then I think with the web as well, we are starting to challenge when the first galaxies started coming in with the theory. So I think that's going to be quite interesting.
We very recently have the tools to do something about this.
Exactly. And then over the next years or so, we are going to keep getting tools to push the boundaries there.
All right. I think a look to the future is always a good place to stop. Thank you very much for all this wonderful discussion. And next month on March 7th, we will have Travis Fisher presenting his take on active galaxies. Please join us then. Until then, take care and thank you for watching.